This research proposes a novel diffusion-based approach for low-light image enhancement, dubbed DiffLL, which leverages the generative power of diffusion models to produce results with satisfactory perceptual fidelity. The proposed method, Wavelet-based Conditional Diffusion Model, WCDM, addresses the limitations of traditional diffusion models, including excessive computational resource consumption, instability, and chaotic content generation. WCDM utilizes the strengths of wavelet transformation to accelerate inference and reduce computational resource usage. By converting the low-light image into the wavelet domain using 2D discrete wavelet transformations, the spatial dimension is significantly reduced, resulting in an average coefficient representing global information and high-frequency coefficients representing sparse details. The WCDM performs diffusion operations on the average coefficient, reducing computational resource consumption and inference time. The model is trained with both forward diffusion and denoising processes, enabling stable sampling during inference and preventing content diversity. A high-frequency restoration module, HFRM, is designed to reconstruct local details by utilizing vertical and horizontal information to complement diagonal details. Experimental results demonstrate that the proposed method outperforms existing state-of-the-art methods, both quantitatively and visually, achieving a speedup of over 70 times faster than previous diffusion-based methods. The authors highlight the limitations of existing methods, including histogram equalization and Retinex-based approaches, and diffusion-based methods, and propose a novel wavelet-based diffusion model that combines the strengths of wavelet transformation and diffusion models to achieve efficient and robust low-light image restoration. The proposed approach is evaluated on publicly available datasets, demonstrating state-of-the-art performance in terms of both distortion metrics and perceptual quality, with potential practical values in low-light face detection. The proposed wavelet-based conditional diffusion model, WCDM, addresses the limitations of conventional diffusion models in low-light image enhancement. By converting the input image into the wavelet domain and performing the diffusion process on the average coefficient, WCDM reduces spatial dimension for efficient restoration. It also adopts both forward diffusion and denoising processes in the training phase, ensuring stable sampling during inference. The training approach is summarized in Algorithm 1, which involves optimizing a noise estimator network via a loss function that combines the diffusion objective function and a content loss function. To reconstruct the high-frequency coefficients of the low-light image, the authors introduce a high-frequency restoration module, HFRM. This module utilizes depthwise separable convolutions, cross-attention layers, and progressive dilation res blocks to extract features and restore the coefficients. The restored average coefficient and high-frequency coefficients are converted into the output image using the 2D inverse discrete wavelet transformation. The network is trained using a combination of loss functions, including the diffusion objective function, detail preserve loss, and content loss. Quantitative evaluations on LoLV1, LoLV2 real, and LSRW datasets show that the proposed method, DiffLL, achieves the highest PSNR and SSIM scores, indicating superior image quality restoration. It also yields the lowest LPIPS and FID scores, demonstrating better visual quality. In terms of efficiency, DiffLL offers a moderate trade-off between performance and computational resources, requiring less time and memory compared to other diffusion-based restoration approaches. On the UHDLL test set, DiffLL outperforms all comparison methods in both distortion and perceptual metrics, showcasing its generalization ability for high-resolution low-light image enhancement. Furthermore, when compared to competitive methods on 5 unpaired datasets, DiffLL achieves the lowest NIQE, BRISC, and PI scores, proving its better generalization ability to unseen real-world scenes. Qualitative comparisons also demonstrate the effectiveness of DiffLL in enhancing image contrast and reducing noise, while other methods often result in underexposed, overexposed, or noisy images. The research paper presents a novel approach to enhancing low-light images using wavelet-based diffusion models, providing a comprehensive comparison with existing techniques such as DICM, MEF, LIME, NPE, and VV on various datasets. Quantitative and qualitative evaluations demonstrate the proposed method's superior performance in terms of global and local contrast, detail reconstruction, and noise suppression, particularly on the UHDLL testset and unpaired datasets. This improvement is attributed to the method's ability to avoid artifacts and generalize well to unseen scenes. Moreover, the paper explores the impact of low-light image enhancement (LLIE) methods on face detection tasks under weakly illuminated conditions. A novel method is proposed that significantly improves face detection performance, enhancing average precision from 26.4% to 38.5% in the high recall area. An ablation study reveals the trade-off between performance and efficiency related to wavelet transformation scale and sampling step. The high-frequency restoration module and loss function terms, including diffusion loss, content loss, and detail preserve loss, are also investigated, showing their crucial role in enhancing image quality. The training strategy, which involves denoising in both training and inference phases, ensures consistency and contributes to the method's superior performance over state-of-the-art methods. However, the paper acknowledges the method's limitations, specifically its performance in extremely low-light conditions, and suggests potential avenues for future research. The research paper presents a comprehensive review of image and video processing techniques, focusing on low-light image enhancement, image restoration, and super-resolution. It discusses the challenges in enhancing low-light images, including information loss and limited generalization capabilities. The authors emphasize the significance of the proposed DiffLL model, which utilizes a wavelet-based conditional diffusion model to produce visually satisfactory results while reducing inference time and computational resource consumption. They also introduce a high-frequency restoration module to complement the diagonal details with vertical and horizontal information for better fine-grained details reconstruction. The paper provides an extensive overview of the literature on low-light image enhancement, including the use of deep learning models, wavelet transformation, and diffusion models. It discusses the limitations of existing methods and highlights the potential of the proposed method in enhancing low-light images for various applications, including face detection, image segmentation, and video restoration. The authors also discuss future work, including extending the proposed method to real-time video enhancement and investigating its effectiveness for other image restoration tasks.